I think is most important to our donor community is thanking you and keeping you informed with what's going on. And that is what we hope to achieve today and in future webinars where you get to interact with our faculty leaders, some of our program directors, and the people who are doing the great work here at the engineering school. So today I get to welcome one of our professors, Hamed Rahmani, an assistant professor in our electrical and computer engineering department. Professor Rahmani we'll share his work around semiconductors, circuits, sensor systems. And what I'll ask is as we go through the next hour or so, allow Professor Rahmani to go through his presentation, share his information. And if there's questions, we can maybe save them for the end or put them into the chat. But Professor Rahmani, thank you so much for joining us. We're beyond excited to hear what you have to talk about and share with our alumni community and our giving community. So without further ado, please take it away.
Yeah, of course. So let me first share my screen. Let me know if you can see.
I see your desktop and now I see your PowerPoint slide. Yes.
Awesome. Perfect. So yeah, hi everyone. Happy to be here, and thank you, Sean and Willem, to organize this event to give me a chance to talk about my research under the title of Intelligent Integrated Circuits and Systems for Sensing and Communication. So as Sean actually mentioned, I'm an assistant professor at the ECE department here at NYU, and in a newly established lab called Research in Advanced Integrated Systems and Electronics, RAISE for short. I'm actually investigating advanced RF and silicon RFICs for intelligent sensing and communication, with a particular focus on RF and millimeter wave and sub-terahertz systems and applied electromagnetics, as well as low power bioelectronics and IoT. Prior to joining NYU, I had the opportunity to work as a research scientist in IBM T.J. Watson Research Center. And before that, I was a design engineer with Qualcomm R&D, working on related topics to semiconductor, wireless, and wireline technology. Okay, looks like the slides are not switching. Okay. Yeah, sorry for the glitch. So at a very high level, the research mission of my lab is to design and implement larger scale and energy efficient integrated systems to address the sensing and connectivity challenges of the emerging applications that I'm going to talk about actually in the next slides. So our approach is to incorporate advanced electronics, photonics, and electromagnetic technologies in order to meet the technical specifications. And because we are targeting a very broad range of applications, these specifications could vary quite significantly. For example, if we just focus on the frequency, bandwidths, and the power consumption, we are dealing with DC frequencies all the way up to terahertz frequencies. And also we are basically satisfying the data rates from kilobit per second all the way up to terabit per second. And similarly, on the power consumption, some applications are extremely low power and require nanowatt level, whereas in some cases, we have to be able to generate multi-watts and efficiently radiate them. Before getting into the technical details of the research projects, I thought it would be very insightful to overview actually the progress of the wireless technology and semiconductor technology, which have not been basically converged since the early days, and see how far along we have come as actually in academic research and in industry. So wireless technology, as is, it was kind of started by Nikola Tesla and Marconi, who are known as the founding father of wireless communication, who successfully demonstrated the first communication back in 1893. And Marconi and his company were the one who successfully actually demonstrated the first transatlantic wireless message being transferred from Cornwall all the way to Newfoundland, over 2,000 miles. In fact, they managed to basically wirelessly transmit the letter S, which was the starting point of wireless communication as we know it. But at the same time, in a separate set of efforts on electronic devices. Transistors, as we know it, it was invented by three scientists working in Bell Labs, not very far from New York, by Bardeen, Schottky, and Breton. And it is basically known to be the enabling point of a vast majority of technological devices and applications that we use now. So starting from 1943, basically the transistor technology was evolved until the invention of an electronic device called MOSFET, or CMOS as we know it today. And it was then that the whole advancement of technology truly was actually started. Let's actually look at what CMOS technology enabled us with. In 1960, the first monolithic IC was designed by Robert Noyce, and you can see actually, you can see the transistors. There are quite a handful of them, and the size is actually quite large. But consider this one and take a look at the state-of-the-art SoC device that we have in consumer electronic that Apple has introduced, M2 Ultra system on chip, that is equipped with 134 billion transistors. So from a handful of transistors, we are now at 134. And if you want to also compare the cost, from a $30 per transistor back in 1960, now we are actually at 75 cents for 100 million transistors. So these numbers basically are a perfect reflection about how much advancement has been done in this area over the past century. But it was not until late 90s and early 2000 that these two technologies basically came together. And that was the starting point of mobile devices and wireless technology as we are basically knowing today. So it is basically interesting to look at the first mobile cell phone and the first generation of wireless technology on the top left, which now we call it the brick because it was quite heavy. It weighed about 2 pounds and it only lasted about 30 minutes of operation when people actually were talking. And it took 10 hours basically to charge. But I'm sure you can basically, compare it with your cell phone's capabilities that you have in your pockets today. And just at a very high level, it is evident basically how different they are. But this is not the end of the story. And today, as a result of advancement in wireless technology and the evolution of 5G and what is expected to happen next in next generation 6G and beyond, wireless connectivity is basically expanding from the mobile phones to every single object around us. And not only that, we are envisioning already a very vast majority of applications. Some of them I have basically, illustrated in this slide, courtesy to Qualcomm, which has provided the roadmap. We actually, in fact, see even some of them in today's live, like from wearable electronics, self-driving cars. These are some of the technologies that have appeared, and they will continue to progress. But it is very important to pay a close attention to the hardware requirement that is needed in order to realize this vision. Different roadmaps have provided different predictions in terms of how many number of connected devices we are going to see. In fact, I have used Cisco, which basically states 43 billion of connected devices by the year 2035. As a result of this massive and exponential growth, we have to be mindful about the underlying challenges of the hardware. I have categorized them into two groups under the sustainability and the data rate requirement, and they are equally important if we want to guarantee a sustainable growth for a future connected device. For the sustainability, every single object that we are basically putting in the environment is consuming power at the first place, and also it has an environmental impact because of the material that has been used in the manufacturing, and more importantly, during the powering approaches. I'm sure everyone knows that batteries are basically the top choices of powering mobile devices. But if we want to stick with batteries and scale it to 43 billion and beyond that, Of course, this is not sustainable because batteries are built from ecotoxic materials and they are going to be absorbed in the environment, which at some point is going to create significant challenges and environmental hazards. On the second side, applications such as self-driving cars and etc., which require very, very fast decision making, are constantly pushing the data rate and the latency. And just to put it into numbers, I want to show you 3 different wireless standards throughout the years and the way they have progressed from the first generation of mobile devices all the way to 5G and 6G. So from 1980s, where we had actually like 9 kilobit per second and a latency that was larger than 1 millisecond, 6G applications are envisioned to require 200 gigabit per second of data rate with a latency that is below 1 millisecond. So of course, these requirements put a massive, massive requirement on the underlying hardware that we are using. And let's say if a decade ago or a couple of years ago, you were able to achieve all of these specifications using CMOS technology, this cannot be continued with only one single device. And heterogeneous integration is emerging as a very hot topic of research and as a solution in order to be able to meet all of these demanding requirements. And what heterogeneous hardware is actually is getting the best of each technology that is out there and allocating those specifications to a particular technology that you want to achieve. And at the end of the day, bringing everything together and assembling everything in the same package to be your final product. So with this background information, I want to discuss specifically what are the design and research challenges on the millimeter wave transceivers, which was one of the major research themes that I talked about. Very simplistic view of a wireless radio is illustrated here, which only shows the front end blocks. And on the transmitter side, the information is up-converted to a high frequency, and by a power amplifier, you drive an antenna which converts the electrical signal to electromagnetic spectrum and electromagnetic energy, and you radiate it wirelessly over the air. And on the receiver side, the antenna captures it, and then you do the electromagnetic to electric conversion. So if you want to improve the performance here, you could consider making your PA and LNA better and making your antennas more efficient in order to extend the operating range. But at the same time, we already established that next generation of mobile devices need you to increase the operating frequency as high as possible, because that's essentially what enables a higher data rate for us. But with this vision, there comes significant challenges, because once the frequency increases, the path loss or the attenuation of electromagnetic waves also goes higher. And it is kind of difficult to maintain the same quality of the signal across distance. Commercial solutions for this problem have been developed based on beam steering and beam focusing, where instead of radiating the energy in an omnidirectional fashion from your antenna, you focus the energy beam to compensate for the increasing path loss. And by controlling the excitation phase to each individual antennas, you are able to steer the beam to the desired direction and maintain the quality actually in the wireless link. So although this technique has been very effective to address high frequency path losses, but what we are seeing as an emerging problem is the heating effect that are associated with the low energy efficiency of the signal generation and signal detection. In fact, as a matter of fact, we know the deployment of 5G technology in 28 gigahertz has been slowed down significantly because of the underlying challenges that they just talked about that are mostly related to the poor efficiency of the underlying circuits. So my research efforts in this area adopts a very holistic view into the design of a radio system and explores circuit level, system level, and component level ideas in order to come up with a co-design approach to guarantee that we have a reliable operation and the energy efficiency concern is completely addressed. So we adopt novel architecture for beam forming and beam steering and explore alternative technologies other than CMOS, in this particular case, 3-5 or compound semiconductor technology, in order to increase our power generation capability at higher frequency. And of course, because we are kind of deviating from a pure CMOS scheme and we are dealing with multiple technologies, packaging and heterogeneous integration is becoming an emerging and very important topic of the research for the millimeter wave transceiver design. So let's actually review at a very high level some of the projects that my group is pursuing on these areas. I'll start with our efforts on the FR3 band, which is a new frequency band that is being considered by FCC to be opened up to commercial uses. Frequency ranges from 7 to 24 gigahertz traditionally has been reserved for specific applications such as satellite and military applications, and it was locked for any commercial cellular technology. But because of the challenges of the higher frequencies, FCC has entertained the idea of opening some empty slots actually in this frequency band to be used by commercial products. And that's actually right off the bat is one of the significant challenges because we are dealing with a very highly segmented frequency spectrum where, for example, you have to be mindful about the interference to the satellite and military radar application. And at the same time, you have to maintain the quality of the service across a very wide broadband for cellular applications as well. So based on this research topic and research motivation, we have started a joint project with my colleagues at NYU, Professor Sandeep Rangan, and Pi Radio Analog Devices and Florida International University to take a closer look into the FR3 band and develop design techniques and problem formulation in order to pave the way for an actual RFIC design and actual wireless radio in next phases. So the challenges that we are dealing with are primarily, as I said, is basically induced by the segmented nature of this frequency band and the fact that we have to be basically compatible with the incumbent application. And we have to be able to cover a very, very broad band frequency range with very low latency. So specifically this project, I'm very happy to actually announce that it was the first funded project by the CHIPS and Science Act budget that was allocated to the development of semiconductor technology. And NYU won one of the very first 3 awards. And it's composed of 4 tasks, and specifically my group basically looks into designing RF conformance and development test in order to characterize at a very high level what should be the hardware and system level specifications if we want to seamlessly incorporate this band into the wireless technology that we have. So in another collaborative project with my colleagues Sandeep Rangan and Elza Erkip at NYU ECE as well, we are looking into co-design hardware and algorithmic approaches that could further enhance the hardware capabilities of a radio front end for this band. So the hope is that by combining the algorithms and by modeling the wireless channels and basically adopting a very holistic view, we could effectively design the hardwares being mindful of the algorithm and the wireless channels and vice versa. So the algorithms are also developed based on the limitations that we are dealing with the hardware design. So because we want to able to enable a beam forming scheme, actually the 3 of the major design goals for the embedded hardware is an scalable RF front end, which I'll discuss it in the next slide, and a very fast switching and tuning capability. So at a very high-level system overview, we envision our system to be modular, where we can have multiple of these RFICs that are tileable and they are scalable. And each single one of them is capable of supporting multiple antennas. So if you want your communication system to cover a wider range, you increase the number of antennas and the RFICs. And with this technique, we'll be able to also scale the transmitted power level and guarantee quality of service for higher frequency bands at the FR3 region. So moving away from the phased array design project, the second research topic that my group explores is the design of 3.5 PA technologies to generate high power at high frequency. Here is a summary of existing integration technology that we have. At the beginning, I briefly mentioned CMOS is the popular choice for many of the wireless designs traditionally in the past decade. But as we go to higher frequencies and require higher power, we kind of see that the CMOS technology's capabilities are bounded with this line that we see. But alternative technologies such as gallium arsenide and gallium nitride intrinsically will make it possible to go to higher frequencies and still able to generate higher power. Knowing this, at the same time, we have to acknowledge the fact that more complex modulation schemes are also becoming a very, very attractive part of wireless communication. So before we were dealing with low order modulations such as like 64 QAM, but long story short, as you start basically making your modulation schemes more and more complicated, one of the problems, active problems that we see is that the signal that you are trying to radiate basically shows a very large peak to average power ratio, which simply means that the maximum amount of the power that your signal has is significantly higher than the average power that is needed to be transmitted from your PA. And I don't want to get in too much into the technical details of that, but in short, if you are basically configuring your transmitter to operate with the peak power, and then you are not feeding the same level of power into the PA, you are wasting resources and wasting power, which degrades your energy efficiency in large. For this reason, with this problem definition, what we are trying to achieve in another project is broadband multipath power amplifier designs that maintain a relatively constant efficiency across different power levels, which are compatible with complex modulation scheme. And the hope is that by enabling this power amplifier that is constant over a wide tuning range, we would be able to address one of the very difficult and challenging approaches in terms of maintaining the efficiency, which is based on the envelope tracking and is the current approach that the industry uses in order to improve the efficiency of their transmitter, to some extent. So another project that my group is exploring is on the smart surfaces that could act as repeaters and that could address the blockage issue that is increasingly becoming more important, especially at the higher frequency. And if I want to give you a very overview of what that problem might be is, remember at the beginning I said beam steering and beam forming has emerged as the solution to compensate the path loss. So in this figure, you see that the user is already in communication with the access point, and that wireless beam has been established between them. But because we are dealing with in a dynamic situation, the distance actually could be changing, and the quality of the signal may drop. So for this particular reason, and even not this, the blockage as another main important considerations, this beam-focused approaches could become problematic. For example, in this case, this line of sight link has been blocked because of the presence of this person. And if we wanted to operate, in a line of sight configuration, we would have lost the signal. I view smart surfaces as a very important and integral part of that vision that was provided at the beginning if you want to go to a ubiquitous connectivity for all the users. And the justifications actually are simple, to comprehend. So once you have this link blocked, you could reroute the wireless channel through a smart surface that receives this beam and reflects it toward your access point. And if we are able to actually add reconfigurability and those capabilities to these smart surfaces, we can guarantee that this link actually is safe and sound once you combine it with the mobility of the user, which are inevitable if you are dealing with a mobile application because you cannot force the users to stay put. And that's why smart surfaces and meta surfaces are becoming and are in fact one of the very important parts of millimeter wave radio design. So I have actually shown another potential use case for these smart surfaces. In the previous slide, we kind of were using those surfaces as a reflector. Or a smart reflector, where upon receiving, we were, changing the direction and re-radiating that. But as we are talking about phased array systems and phased array antennas that must have basically great focusing capabilities, sticking with the traditional approaches where you have a phase shift per element is actually quite challenging and might not be scalable if we are targeting thousands and thousands of antennas because of the limitations in the wiring and in the phase shifter itself and high frequency components. Using the meta surfaces, could be a potential solution for those limitations because in this configuration, you don't have to route every individual antenna to a signal source, and you could use the meta surface as a basically transmissive plane that receives this electromagnetic energy that is coupled to it in near field operating region. And by adding individual programmability to individual elements on the surface, we potentially could program the far field radiation and steer this beam at the desired location. So the same idea could be applied to the receiver. So we view this technique and this idea as potentially a very effective solution to address the limitations of phase shifter and beamforming technologies as we know. So far, my talk primarily covered, connectivity in the application domain that we are pretty much used to, but the capabilities of these technologies are much more beyond just connecting your cell phone to the cloud and to the access point. In fact, brain-machine interfaces have been one of the topics that have been explored quite, rigorously over the past few years. And there is a lot of excitement in this area. And I'm sure basically you have heard a lot of news about the clinical trials and some of the clinical demonstrations. But what I view as the total and ultimate power for the semiconductor technology to help the medical applications and closed loop therapeutics, is illustrated basically in this image. Imagine the case that we can enable simultaneous recording of neural activity across thousands and thousands of electrodes across the human brain. And these SoCs that are system on chips that are implanted are capable of digitizing those neural activity and transmitting them back for a reader to process them. At the same time, in order to basically make sure that we are not employing toxic batteries that are pretty much large in terms of their footprint, we are exploring wireless power technology from conformal metasurfaces to the individual distributed SoCs. And the ultimate vision that we have is enabling a distributed network of neural recording devices that would enable basically an unprecedented recorded data in order to, first of all, basically enable neuroscience in general, because the lack of enough information has been the gating factor in getting to know the complex nature of the human brain. So this project, at a very high level, if I want to categorize it into two sub-projects, is composed of the wireless power delivery to the individual implants, which provides a DC voltage that can be used to power up the internal circuitry. And once we have that power, we can use it to enable this data transmission, which is an ultra-wideband data transmitter that enables multi-gigabit per second of communication bandwidths from the human brain to an external recorder. And of course, we have to address the signal acquisition and the digitization part of it. So with these three major fronts, my research group's effort on the biomedical and bioelectronic IoT is basically, pursuing to implement and deliver this goal. But there are, of course, a lot of technical challenges and fundamental barriers that has to be addressed in order to get there. I'll start with the wireless power transmission to miniaturized implants. And just to give you an idea about what are really the challenges here, I have shown the thermal absorption of biological tissues at two different frequencies, 500 megahertz and 2 gigahertz. So what the results are revealing is that at one point, you would like to increase the power transmission frequency to a low gigahertz range, because that's when you are enabled to use miniaturized antennas and reduce the size of your system. But at the same time, as the frequency goes higher, the thermal absorption in the tissues is increasing. So which creates actually a dilemma. How high I should go and what is the safest frequency that I can operate these devices at and still, deliver a meaningful amount of power. We have been extensively, studied this problem through a lot of simulations and analytical results. So I'm going to skip some of the details here, but here is basically the analytical framework that we developed, and we analyzed the efficiency of the wireless link. But at the end of the day, what was concluded was if you want to have a millimeter-sized SoC and power it through electromagnetic waves, the safest amount of power that you can deliver is bound to 300 microwatts roughly. While at the same time, we know that our internal circuitry actually are much more power hungry. In fact, this is a typical power consumption that is needed by a continuous neural recording, which is in the ballpark of 4 milliwatt. So our research efforts in the wireless power delivery actually have been trying to address this discrepancy between the power requirement and the maximum power we can deliver to an implant. So we designed a power management unit on an integrated system. that was successfully receiving the electromagnetic energy through an external link and converting it to a DC voltage. And by including this power management unit, we were making sure that the operation of those power-hungry building blocks is duty cycle, meaning that if they are only activated for 10% of the time, the average power consumption actually is 10 times lower. And our millimeter-sized radio is in fact capable of, driving them. So based on this idea, we fabricated this integrated circuit as shown on the left. You see that it has two antennas. Everything is implemented on chip, which means that this system, by a form factor of 2.2 by 2.4 millimeter, could independently operate while implanted. No need for external batteries and no need for, post-process assembly. So the form factor reduction actually showed a 7-fold improvement over the state of the art. And by incorporating advanced co-design circuit techniques with the antenna, our prototype achieved actually a 4.7 picojoule per bit energy efficiency, which was 2.3 times higher than the state of the art at the time of the publication. But in this project, as I said, we incorporated basically simple power transmitters, and our vision is to expand the capabilities of the power delivery by exploring the metasurfaces, because metasurfaces essentially will enable us to control the design and the current profile at the receiver site. And essentially, it could be viewed as a very effective method to suppress the thermal absorption of the biological tissues. So the hope is that once the thermal absorption issue is addressed, our power delivery capability to this millimeter-sized system basically scales to milliwatts and tens of milliwatts, and then we can expand what are the functionalities that we can achieve with a millimeter-sized system. So just an overview again, I talked about the millimeter wave approaches that we were pursuing, and the project that I talked about on the bioelectronics was one of the very few projects that in the past and currently we are exploring. But building upon these capabilities, there are alternative approaches and alternative applications that we are also interested in. I talked about the metasurfaces briefly in the previous slides, but IoT is going to be another interesting and important, equally important topic with a huge potential societal and commercial impacts. And if we dig deep into all of these 4 domains, energy efficient sensing and connectivity is the overarching basically requirement and the theme of all of these topics. On the IoT side, what we envision is by building these powerful and miniaturized integrated circuits, we could distribute many and many of them into an environment and leverage the powers that we can get by scaling the capabilities of one chip to thousands and even beyond that. And one of the very good design examples that perfectly captures what those capabilities might be are coherent power combining that I am trying to basically explain at a very high level in this slide. So imagine basically you have many people in a room that they are all talking, but they are not talking about the same topic and they are not talking about the same subject. So what we hear actually is this fainted noise, which is very hard to pick. So you cannot like tune in on one person and try to listen to them. So in fact, that example is a perfect, analogy to what's happening if you have multiple of these sensors that are distributed in the environment, but each one of them is operating at a different frequency with a different phase. If you sum up all those signals, you have this abstract form, which if you plot the frequency spectrum, you see that the power basically is pretty weak and nothing is detectable. So we asked ourselves this question that what would happen that if we kind of forced all of these sensors to talk at the same time, or another way to be synchronized. So if that happens, because the frequency is the same and the phase is the same, eventually with n sensors in these clusters, our amplitude is amplified n times, which if you think about in terms of power, we are getting an n square amplification in terms of the power of the received signal at the receiver. So with this idea, we envision that we should be able to synchronize and form a scattered array and be able to detect very low signals from these individual distributed SOCs at a very large distances, which could potentially enable applications such as localization and discovery of oil reservoirs and rescues. These are like some application levels, but of course, the technical specifications of each one of them could vary. So the idea here was that we use this, transmitter to transmit the power and the synchronization signal to the sensors in this cluster. Once the sensors are powered up and they receive the synchronization command, they all start to talk back at the same time at half of the frequency. And as a result, we should expect to receive a much stronger signal at the detection location. So, and to test this idea, we fabricated these integrated chips, and in this measurement setup, you see that we have 4 of them combined, and the performance is characterized in 2 cases. One when there is no synchronization signal, and one with the presence of that synchronization signal. And the measured spectrum basically, perfectly backs up our idea. You see that at the absence of that signal, you have 4 relatively weak tones that are operating at different frequencies. But once you start giving that command, all of these sensors basically come together and they start basically transmitting a unified tone, which is 14 dB larger in terms of the power. And 14 dB basically could go long way in order to extend the operating range of your radio. But this is not the end of the story. Beyond IoT and beyond connectivity, we do see great potentials for low cost and ubiquitous system-on-chip platforms when it comes to point of care and healthcare applications. In one of our previous efforts, we explored the feasibility of chronic wound and skin monitoring application enabled by these IC platforms that we were developing. And just to test that idea, we collaborated with a group of medical doctors, and we successfully demonstrated that by measuring the electrical characteristics across different types of wounds that are inflicted with different mechanisms, we are able to record and post-process with the power of machine learning and hopefully in the future AI to have a better understanding about the healing mechanism and about the specifications of each individual types of wounds. So what that study basically showed us was this dielectric constant was sufficiently enough for us to categorize different types of wounds with an accuracy higher than 96% to detect what has been the source of that wound. But of course, this is just the beginning, and you could imagine so many different point of care and lab on chip products that could benefit from a very low cost and long-term sensor that patients could wear with minimal form factor and minimal interference with their daily lives. And it could also serve as a very important source of information in order to provide that data to a medical doctor, as opposed to going to the doctor very infrequently and then recording your patients basically biological signals and aptitudes. So this captures basically at large what some of the research projects and the future directions at my group pursue. But for the last slide, before I conclude the talk, I wanted to talk about the collaborative research opportunities that would be enabled based on the vision and the great educational impacts and societal impacts that some of these topics basically could open up. So in the recent passage of the Chips and Science Act, we already see that there is a very great emphasis on workforce development because all of these emerging applications that I talked about, and some of them I didn't get the chance to talk about in this talk, require a skilled developers that can design interdisciplinary hardware prototypes to effectively address those needs. Remember, 3-4 decades ago, where the wireless communication started, the connectivity concept was just, captured in a cell phone, and it was the design requirement basically was probably much simpler than now, that the electromagnetic knowledge, the knowledge of the materials, biology, and everything has to be basically considered by a designer in order to guarantee the success of a product. So such an interdisciplinary research requires an interdisciplinary education as well. So I'm hoping that, by training interested students at NYU, we would help to train a group of skilled developers for the next generations of hardware, which at large is essential to maintain US's leadership in semiconductor sector. Also, because of the interdisciplinary nature of these projects, I think they are very ripe to attract interested students at high school levels and undergraduate students. So equally, I'm very supportive of fostering the education of underrepresented minorities, and bring them to my research group to receive the mentorship and the education that is needed to get them at a level of success needed to pursue STEM careers or graduate studies. Also, I wanted to briefly mention the potentials behind this project when it comes to technological transfers and entrepreneurship, which I'm very happy to see that NYU already has focused centers that are supportive of these ideas, and entrepreneurships are encouraged. But also, being affiliated with NYU Wireless, I have this chance basically to interact with industry pioneers in wireless industry and wireless power transfer. And the hope is that we'll be able to work with each other in order to at least, expand the capabilities that we see in the research and enable the commercial uses in people's daily lives. But aside from that, again, I want to highlight the interdisciplinary nature of this project because it's very important that we consider that this is very ripe to close the knowledge gap that we do have between engineering, neuroscience, biology, and signal processing. So I view some of these topics to be the enabler of collaborative and high impact research projects. And my hope is to work with my colleagues at NYU and beyond NYU in a School of Medicine and different engineering departments to realize the visions that are provided here. So with that, I would like to stop, and I thank everyone for your time and attending this talk, and happy to answer any questions you might have.
Professor Rahmani, thank you so much. I am encountering a bit of video difficulty, so I will keep my video off. But thank you again for that. For those on the webinar, if you have questions, put them into the Q&A portion, and I can read them to Professor Rahmani, and we can answer them in real time. But maybe as people are thinking about typing in some questions or things, you talked a lot about the energy efficiency or the energy consumption of these devices. Are you all starting to think about like the carbon footprint of the devices as maybe some other consumer goods are, to begin to think how can people make a more sustainable decision and some of the things that they buy, even though so many are kind of embedded within our phone devices and other things where we may not actually know?
Excellent question. That's actually a very important point, and I'm glad that you asked it because in one of the papers that we published in the Journal of Microwave, so I probably don't remember the exact title, but it was Sustainable Next Generation IoT Devices. So we are talking about those aspects exactly. So manufacturing is one of the topics that has been discussed, and the carbon footprint, and the choices of the materials and how we want to use alternative materials that kind of address that has been discussed. Just to give you an example, one of my colleagues, one of our collaborators actually in an Italian university, they were working on this circuit boards that are implemented on a paper substrate rather than the FR4 substrate that is the go-to choice for many of these circuits. So the idea was that, once this IoT nodes that are kind of like for one-time use, you are done with them, even if they are not collected properly, because they are built with paper, they're going to be absorbed into the environment like much better than an FR4 board or a plexiglass that will take decades to get absorbed.
Okay, terrific. Again, no new questions. Oh, we have one question in. The question is, how long will it be before we can see things like point of care monitoring for healthcare?
Again, another very good question. So, I believe like it's just more than being a matter of enabling the individual technologies that are needed for that. I think a meaningful collaborations that are bridging from engineering to biology is the real requirement that has not been done with the amount that is needed yet. So because it is requiring like multiple expertise, from mechanical engineering, from bioengineering, and from electrical engineering, I think if that happens, that close collaboration happens, and engineers and researchers really want to get there, probably we will see that technological barriers that we are concerned about, it might be much sooner than we expect. But this is just my 2 cents on that. Of course, unless this close collaboration happens and those requirement gets uncovered, providing a very specific answer or a timeline for that would be difficult. But at least my hope is we are really hoping that it happens soon. So fingers crossed.
And we have about time for one more question. If no one puts one in the chat, I'll at least ask one. Congratulations for being one of the first award recipients for the CHIPS Act. How do you see the CHIPS Act playing a role in the future of higher ed research, higher education research, and the way that they've been seemingly creative with this higher ed research pipelining into industry application?
Excellent question. I think I'm really happy to see that happen, because I'm just quoting NatCast's director. Actually, there was this webinar and talk happening like less than a month ago. So what US's industry basically, with the current rate of absorbing students and the way that the technology is progressing, he was saying that probably we are going to see 30,000 short of engineers if we do not address this problem in near future. So I might be a little bit fuzzy on the exact number, but this is what I remember. So in the CHIPS Act, workforce development has been one of the very major themes that is being encouraged and being highlighted. And the hope is to attract the students, high school students and undergrad students, basically to come and study STEM fields, electrical engineering, and we have a pipeline of students going through in order to address what future industry requires. So CHIPS Act being on its first year, we have to see basically, how successful it gets in addressing some of those concerns, but it's a great start, and it's one of the fundamental, pillars of attracting students, because the ask is there and the mass is certainly there. But in terms of execution, we have to see.
Well, this is terrific. We are nearly at time today. Professor Rahmani, thank you for giving us a small snapshot of the work going on with your lab, being led by you and your great students. We're grateful that you got to share this information with our donor community, and we look forward to continuing to see your career progress here at NYU Tandon. So thank you again. We are grateful for it, and for all those in attendance and all of our donors and supporters, we are grateful for your support. It allows Professor Rahmani and his peers to continue to have an impact on direct student impact with scholarships and broad research initiatives as well. So with that, we wish you all a wonderful day. Thank you very much.
Yeah, thank you. If among the audience, if you have any questions, I believe Sean would pass my information and I'd be happy to answer.
Absolutely. We will.
Yeah, have a good day. Bye.
Yeah.